Hi, my name is Ariana Gagnon, and I am a fourth-year grad student at Cornell University in the Chemistry and Chemical Biology department.
My name is Jan Balaika. I'm a postdoc at Cornell University in the Department of Chemistry.
And today we're going to be showing you the kit surface area and reaction rates that we helped design, and we hope you enjoy. So in this kit, you'll receive a folder of materials that'll help you guide the activity. In this folder includes a materials checklist for all the materials for all of the activities that you should use to make sure you've gotten all the materials, and then you can also return them after you're done using the kit. There's also a teacher handout that you can use to help guide your lesson, and it provides you some more information on the chemistry behind the kit. And then there is also a worksheet, activity sheet for the students that will help guide them through the lesson that they can fill out and you can use for an assessment to gauge their learning. There is also a presentation on the website that is currently live that you can access for free at any time to help guide your lesson as you present it to the students.
So the first activity we'll do is using a flower and a flame to get kid to think about how surface area affects reaction rates. So you will receive a tube and a funnel, a box of flour, plate, candle, and a lighter. So the first part of the activity is trying to put on fire just a pile of flour. And before you do that, you can ask the students whether flour is flammable or not. And as you can see, it burns, but very slowly. It just turns black, but there's not really a flame. So how would this change? Instead of pile of flour, we will use a fine mist of flour. And we can create that by putting just a small amount of flour into the funnel here, and blowing across the flame of the candle. So you might want to aim on the top part of the flame. Yeah. See how it burns. You might want to practice with that before you do it for the first time, and you make sure you wear safety goggles.
So after you've done the flower fireball demo, the students will have had an opportunity to fill out their worksheet, making a hypothesis how the pile of flour versus the flour cloud is combustible with fire. And this can lead into a hypothesis where they discover surface area affects the rate of the reaction. And they can test this in the next part of the kit when they do the Alka-Seltzer rockets. So now that the students have looked at the flower fireball demo, they'll move into testing their hypothesis of how surface area affects rate of reactions in the next activity, Alka-Seltzer rockets. So here, what they'll do is first write down their hypothesis of how fast they think their reaction will go with solid or crushed Alka-Seltzer tablets. Once they've had a moment to write down their hypothesis, we suggest reading over the instructions for the activity before starting, which are here in their activity sheet. So for this activity, the students will get a fourth of an Alka-Seltzer tablet. One will be solid for the reaction and one will be crushed. For the first part of the experiment, we'll do the solid Alka-Seltzer tablet. The students will need to measure out 10 milliliters of water before starting. And they will be given a 10 milliliter graduated cylinder to measure this out. And you can use any cup or beaker available to you to give the students the water that they will then measure out. Lovely. So now that we have our 10 milliliters of water, we will then do our next step, which is to add the solid quarter tablet to the film canister, which is not in there right now. So So this is about a solid fourth of a tablet. Go ahead and add that to the foam canister. So the reaction that's occurring in the Alka-Seltzer mixed with water is that the Alka-Seltzer tablet actually contains baking soda and citric acid in solid form. But when those two chemicals are dissolved in water, they react, and one of the products of that reaction is CO2 gas. So when carbon dioxide gas builds up in a closed container, such as a film canister, it will eventually cause the top of the film canister to pop off. And the students will measure how long it takes for the reaction to produce CO2 gas to cause that lid to pop off. The way that they'll measure that is using a stopwatch. Now the kit does not include a stopwatch, which is why we suggest if the students have access to a phone that they could use their phones to measure the reaction rate, or you as the teacher can use a stopwatch on your phone or one that is easily available to you. Okay, and with that, we'll do the first part of the reaction. Jan, could you hold the film canister?
Sure.
Thank you. 3, 2, 1. Make sure the top is on tight. Wow! Oh my gosh! Wasn't that exciting? So our reaction took about 30 seconds, and your reactions will probably take about that time, maybe even between 30 to 45 seconds. And the students can record that reaction time on their results table in their activity sheet. So we do want to make a note, though, that sometimes these containers, if the top is not on tightly, then there might be some gas leakage and there won't be as much of a buildup in pressure within the film canister. And if that happens, the reaction time can go as long as 1 to 2 minutes. So please be aware of that when the students are doing the reaction and tell them to be patient. Now that the students have done their first reaction with a solid tablet, they can repeat that experiment twice, so they get 3 sets of data. This will teach them the importance of replicating their data to see if the result they see is actually real. And once they've recorded those 3 different times, they'll have an opportunity to average that time for the solid tablet and also note observations in the results table. So now we'll move on to the crushed Alka-Seltzer tablet. So Jan has already taken a quarter tablet and placed it in folded paper. He has crushed it using the bottom of the film canister, and you should tell the students to do the same. Excellent. So now that we have our crushed tablet, we're going to go ahead and add it to our film canister. It's important to add the tablet first, so that when you add water, it will allow a mixture to occur, and the reaction will be more complete. So like we did before, we're going to measure out another 10 milliliters. And just to reiterate, when we add the water, we should quickly seal the film canister and make sure that the top is on tightly to avoid gas leakage. Ready, on?
Ready.
1, 2, 3. So after the students have had a chance to do their 3 trials for the solid and crushed Alka-Seltzer tablets, they will look at their data and calculate the average time it took for the solid and crushed tablet to react and have the cap pop off. For us, our data shows that we had an average of 47 seconds for the solid tablet and an average of 20 seconds for the crushed. And here are some observations that we noted. So for the solid, the second trial was 67 seconds, and that was a little long, so we made a note that it was a little longer than the other 2 trials. And for the crushed, there was a trial that was a little longer than the other 2, so we also made a note that there was some gas leakage in that trial. Once the students have filled out their table, they'll have an opportunity to graph their results. So the graph will be on page 4 of their activity sheet. They can graph their individual trials along with the averages for each trial. And they'll graph the averages in a different color compared to the trial data. So once the students have had an opportunity to graph their data and discuss with their fellow classmates what their data means, they will likely see that as the surface area of their Alka-Seltzer tablet increases, so does the rate of the reaction. And now that they've had an opportunity to experimentally test this, they can understand why this happens at the molecular level in the next activity, bonding belts.
So in the final activity, the student have a chance to understand what's going on at the atomic level. Each of the students will present one atom, and they will be given these bonding belts they can put around their waist. And the belts have colored stripes with a Velcro at the end. They can use the stripe to connect with another atom, creating a chemical bond. They can create only one bond per person, and up to 3 bonds total. Children in the class will be divided in two groups. One group 1/3 and the other group 2/3 to have different sizes, and they will try to maximize the number of bonds within the group. In the end, they will count the number of bonds, number of people, and calculate the ratio of bonds per person.
So now that the students have done the bonding belt activity, they should have an opportunity to fill out their data table, like we have done so here. So for the data table, we have the 1/3 group, 2/3 group, and then when they combined, the 3/3 group data. In this data, we'll start talking about the 1/3 group, where we had 6 atoms or people who made in total 8 different bonds. So when we did the ratio of bonds per atom, we got the number 1.3, which the students would hopefully realize that this ratio is smaller than the other 2 groups. So this ratio actually demonstrates that as we have less bonds in a smaller group, there is a smaller energy needed for reaction of this small group with a reactant. This is similar to the crushed Alka-Seltzer tablet reaction that they did in the previous activity, as well as the flour fireball. But as we increase the group size, such as the 2/3 group, this ratio ends up going from 1.3 to 1.5. Thus, the energy requirement for reaction with the 2/3 group increases. And this is similar to the solid Alka-Seltzer tablet, as well as the pile of flour in the flour demo in the beginning. And then when the students recombine, the data will resemble that of the 2/3 group and maybe even be a little larger. Here we got a slightly lower but still similar ratio of bonds per atom to the 2/3 group, of 1.45 for the 3/3 group. So another observation that the students might notice when doing this activity is if they are in the larger groups, they may realize there are some students who are enclosed by a circle of other students, and they themselves, as an atom, are unavailable for reaction with the outer environment. Now we realize this is a lot to take in, which is why we made notes in the teacher handout explaining exactly what types of observations that you can make in this activity for the 1/3, 2/3, and 3/3 group. After the activity is over and they've had an opportunity to discuss with you and their classmates, they can start filling out the long response answers in their activity sheet. Once the entire activity is finished and they've had an opportunity to fill out their answers, you can also do another flour fireball demo to see if they've, to assess their learning process from the beginning of the workshop to the end. So we hope this kit helps you in teaching your students about reaction rates and how surface area affects it. We took time to make sure that this kit reaches next generation science standards, and we love to hear feedback, so hopefully this helps and your students learn a lot by using our kit.